All right, so this is an ALEKS topic that's called finding a molecular formula for molar mass and element something, I'm not really sure, but it's this one. And this is a great problem. It's a mass percent type problem first, and then it's an empirical formula type problem first, and then it's a molecular formula problem as well. So it's sort of two problems in one. So the first part of this question, so we're given the molar mass of 230.30, but we're going to put that aside for the beginning of the problem, and then we're going to look at this mass percent information. So immediately when I see mass percents, I'm going to assume 100 grams, and that just makes the calculations a little bit easier. It makes the start of the problem go a little bit faster. So if we assume 100 grams and we have these mass percents, well, we can just convert those mass percents into numbers of grams. And that's why I like doing that. So 62.58%, that gives us 62.58 grams of carbon, 9.63 grams of hydrogen, and then 27.79 grams of oxygen. You don't have to assume 100 grams, you could assume something else, but this just makes this calculation much more straightforward. I'm going to convert each one of these into moles, so 1 mole over 12.01 grams for carbon, 1 mole over 1.01 grams for hydrogen, and then 1 mole over 16.0 grams for oxygen. And then we'll get our different numbers of moles of each of those elements. So 5.21 moles of carbon, 9.53 moles of hydrogen, looks like I forgot to write moles here, and then 1.74 moles of oxygen. So once we have these numbers of moles, this is where we're going to be comparing the ratio of carbon to hydrogen to oxygen. We can't do that over here because the numbers of grams is not the count of how many carbon atoms we have, how many hydrogen atoms we have, how many oxygen atoms we have. That's the number of moles. So we need to do this exercise first so that we can compare the number of moles. Now, the way that I would set this up, what we're really looking for is a ratio of carbon to hydrogen to oxygen. And I'm going to set the ratio of oxygen to 1. And the reason I'm choosing 1 is because it's the smallest number. Out of these three choices, 1.74 is the smallest number. So basically, I'm going to compare the carbon to oxygen ratio and then hydrogen to oxygen ratio to figure out what that is essentially. So if you take 5.21 and you divide it by 1.74, that's going to tell you what the ratio of carbon to oxygen is, and that comes out to be just about 3. So my ratio here I would put in as a 3, right? It's a 3-to-1 ratio between carbon and oxygen. That's what this calculation essentially tells us. We can do the same thing for hydrogen, 9.53 divided by 1.74, and that equals 5.49. We can round that to 5.5. I think that that's a fair thing to do. And that's going to be the ratio of hydrogen to oxygen. So the ratio that we end up with is 3 to 5.5 to 1, and that's really based off of these numbers here. Obviously, we can't have 5.5 of a hydrogen atom. So I'm going to take all of this and multiply the whole thing by 2. So my empirical formula is going to be C6H11O2. So that's my empirical formula based off of these mass percents, just a typical type of empirical formula problem. Now in this case, we're adding in one more aspect. The molar mass of our compound is 230.30 grams per mole. Now our empirical formula, this is the lowest ratio of carbon to hydrogen to oxygen in our compound. So the empirical formula might be the same as the molecular formula, that's possible, or it might be, the molecular formula might be a multiple of this empirical formula. So the way to figure out if this is the actual molecular formula is to calculate what the mass of your empirical formula is and then compare that to your molar mass. So if we go ahead and calculate the molar mass of this empirical formula, the mass of this ends up being 115.17 grams per mole. So that's my empirical formula, just adding up, C6H12O2. I end up with this mass here. If this is my mass of my empirical formula and this is my mass of my molecular formula, well, it's pretty easy for me to see this is a 2-to-1 ratio. Basically, my molar mass, my molecular formula should be twice as big as my empirical formula. So my molecular formula should be C12H22O4. and I'm just doubling my empirical formula. My molar mass, if I calculate this, will be the same as this 230.30. And the ratio, what's really important here, right, is the ratio of carbon to hydrogen to oxygen stays the same throughout this entire process. So this would be my final answer, molecular formula C12H22O4. And hopefully that process makes sense. First, we're finding the empirical formula. Once we have the empirical formula, finding the mass of the empirical formula, and then comparing that mass of the empirical formula to the mass of the molecular formula, the molar mass, and then figuring out what sort of ratio I need. In this case, it's a 2-to-1 ratio, so I'm just doubling my empirical formula to get to my final molecular formula. All right.